Limits at infinity and horizontal asymptotes. Limit at infinity. If, as x moves towards infinity, f of x gets arbitrarily close to a real number L, then we call this a limit at infinity, and we write the following limit notation. So x values are approaching positive infinity. If we direct our attention over to the graph, if we think about x values are going towards positive infinity, what's happening to the y values? What's happening at the end of the function over here? So here we can see that my y values are getting closer and closer to this y value L. And we can also think about what happens as x moves towards negative infinity, and then we would use the notation x approaches negative infinity. So the main idea is that limits at infinity describe the end behavior of a function. What is happening at the ends of a function? Let's go ahead and take a look at an example. So we're going to consider the function f of x equals 1 over x, and we're going to think about it in two different ways. We're going to take first a numerical approach. So we want to think about what happens when we start to plug in bigger and bigger numbers as x heads towards infinity. So you can see this column on the left, x values are going up by multiples of 10 each time. So if I think about what happens when I plug in these respective x values, I have 1 over 1, I get out 1. If I plug in 10 next, 1 over 10 is 1/10. If I plug in 100, 1 over 100 is 1/100th. If I plug in 1,000, I get 1,000th. So I can start to see that as I substitute in bigger and bigger numbers into 1 over x, the x is in the denominator, the overall fraction gets closer and closer to 0. So these numbers are getting really, really small, and they're getting closer to 0 as I start to plug in x values that are getting bigger and bigger. So let's summarize what's happening down below. So x values are going towards infinity, and the f of x values, or the y values, are getting closer and closer to 0. So we can go ahead and compare that to a graphical approach. We'll focus on what's happening as x goes to positive infinity. So over here is positive infinity. I can see what's happening is that my function is getting closer and closer to the x-axis over here, which has a y value of 0. So over here, the limit as x approaches infinity of 1 over x is 0. I'm approaching the x-axis on the top of the x-axis, so with positive values that are getting closer and closer to 0. If I go back and take a numerical approach to plugging in negative values, if I plug in -1 first, 1 over -1, it's -1. If I plug in -10, 1 over -10 is just -1/10. So I can see that my numbers are still getting smaller, the y values, so -100th, -1000th. So I can see these numbers are getting really small as well. They are also getting closer to 0 as I start to plug in these numbers that are heading towards negative infinity. So if I go ahead and summarize what's happening in this table, as x values are going towards negative infinity, once again, my function values are going towards 0. And we can go ahead and compare that to what's happening on the graph of 1 over x. So as I start to head towards negative infinity, if I go ahead and analyze where the function is getting close to, it's getting closer and closer to 0, but underneath the x-axis where values, the y values, are negative. So I'm still getting closer and closer to 0 though, so the limit as x approaches negative infinity of 1 over x is 0. Now let's go ahead and take a look at this theorem. It says that if r is a positive rational number and c is any real number, then the limit as x approaches positive or negative infinity of c, so c was a real number, over x to the r was any positive rational number, that whole limit has to equal 0. So let's think about what's happening for a second here. We are having a fixed value in the numerator, some constant number c, and the denominator is x to a positive rational number. So what's happening is if I plug in values towards positive or negative infinity into x, the denominator is getting really big and the top is staying constant. So if the denominator starts getting bigger and bigger and bigger, so if I start to get 1,000,000, 1,000, 1,000,000,000,000 in the denominator and the top stays constant, then that whole fraction is getting smaller and smaller and getting closer to 0, similar to the example of 1 over x. So instead of 1 over x, if it was 2 over x, the constant on top doesn't change anything. And it turns out that it doesn't have to be x to the first power. X can be raised to any positive rational number, and this will still happen. So in words, what's happening is if the denominator is getting bigger faster than the numerator, and in this case the numerator is constant, then the entire fraction is going to go to 0. So if the denominator gets bigger faster than the numerator, the entire fraction goes to 0. Alright, let's go and do some examples. Let's evaluate these limits at infinity. So x is approaching negative infinity, but what I have on the top is I have a constant, and then I have x to a positive rational number on the bottom. So this whole fraction is going to 0. So if I think about it, the denominator is being raised to the 5th power. These big numbers are being raised to the 5th power, and the top is staying constant. So these numbers are going to get close to 0. If I take a look at the second example, x approaches infinity of negative pi. That's still a constant. And then on the bottom, I have the cube root of x squared. So another way to write this is x to the 2/3. So I have a rational number, a positive rational number as my exponent. So this is still going to end up going to 0. So I have a constant over x to the 2/3. So the bottom line is that the bottom, the denominator, is getting really, really big, and the top is staying the same. So that fraction goes to 0. And then in this third example, we have the limit as x approaches infinity of 5x over x to the 3rd. So here we can actually do a little bit of reducing, so we can write this as the limit as x approaches infinity. The x's in the numerator and denominator will cancel, one copy, so I have 5 over x squared. So here, again, I have a constant, and then x to a positive rational number, so the whole fraction does go to 0. But something I want you to just kind of notice right now is that we didn't have to reduce the fraction so much as understand the concept that in the denominator of this last example, I have a cubic function. I have x to the 3rd. So that denominator is going to get bigger faster. If I cube numbers, they're going to get bigger faster than if I just take numbers in the numerator to the 1st power. That whole fraction is still going to end up going to 0 if the bottom is a bigger number than the numerator ends up being. So that's just something to keep in mind. Let's go ahead and formally define horizontal asymptote. A line y equals b is a horizontal asymptote of the graph of a function y equals f of x if either the limit as x approaches positive infinity or negative infinity equals this y value b. So in other words, if we're ever told find all the horizontal asymptotes of a function f of x equals, that's the same as being asked to evaluate the limit towards positive infinity and the limit towards negative infinity. In this example, we want to write an example of a limit for a function f of x that indicates f of x has a horizontal asymptote at y equals 4. And part B, we want to indicate f of x has a vertical asymptote at x equals 1. So the big picture here is we're trying to figure out, well, what's the difference between a limit at infinity versus an infinite limit? And we'll think about this graphically. So a limit at infinity is all about what's happening towards negative infinity and positive infinity on the graph. If I end up getting close to a real number L, then I have a horizontal asymptote at that value L. So for part A here, if I want to indicate, if I want to tell somebody the graph of f of x has a horizontal asymptote at y equals 4, I'm going to go ahead and write that the limit as x approaches either positive or negative infinity of f of x equals 4. So I could also have written negative infinity. Either one will work. So write an example. This one satisfies it just fine. So now thinking about that, the difference between that and an infinite limit. So an infinite limit corresponded to a vertical asymptote. What that meant was that as x approaches c from the right on this example, my y values are going up to positive infinity, or c from the left, sorry it's kind of small and blurry, is going down towards negative infinity. So if I have either one of these situations happening, as I approach a real number from either the left or the right, if I approach positive or negative infinity, I now have a vertical asymptote. So here, I'm going to go ahead and construct a limit that tells somebody that f of x has a vertical asymptote at x equals negative 1. So I have the limit as x approaches negative 1. So I could write from the left, from the right, I could even put a two-sided limit. So I'll leave it as a two-sided limit. The limit as x approaches negative 1 of f of x equals infinity. So essentially what I'm telling somebody, if I drew a little sketch of my graph, is that at negative 1, both sides are heading up to positive infinity. Whereas part A said that as I approach positive infinity, here's 4, there's a horizontal asymptote there. So other stuff might be happening, but at the end of the function, my graph is getting closer to 4. Now, it might even cross over 4, right, bounce back and forth, but as long as it gets close to 4 at the ends of the function, or at the right end of the function towards positive infinity in this particular case, then I have a horizontal asymptote. Let's go and do an example where we sketch a function, f of x, that satisfies all of these conditions. So the limit as x approaches 3 equals infinity. So here what we have is something that represents a vertical asymptote. As x values get close to 3 from both sides of 3, my y values are going up towards positive infinity. So I'm just going to keep it tight and narrow around 3 for now until I figure out what else is going on the graph. As x approaches negative 2 from the left, my function's approaching positive infinity. And as x approaches negative 2 from the right, f of x approaches negative infinity. And so just looking kind of ahead, there's nothing else that's going on between negative 2 and 3, so I'll just kind of keep that in mind. So as I look at negative 2, I do have a vertical asymptote there, and there's different behavior on each side. So as I approach negative 2 from the left side, I'm going up towards positive infinity. And then as I approach negative 2 from the right-hand side, so from the right side of 2, just barely to the right, coming towards negative 2, I go down to negative infinity. And as I said, in between negative 2 and 3, we have flexibility. I can just go in and connect this however I want, just making sure I still have a function. I pass the vertical line test. And then looking at the next one, the limit as x approaches negative infinity of f of x equals 2. So this describes what's going on as x values go towards negative infinity. So this one is a horizontal asymptote. So these two described another vertical asymptote. So towards negative infinity, my y values are getting closer to 2. So I'm going to pick up where I left off here, and I'm going to head towards 2. So I'm going to approach 2 on the left-hand side, so I do have this horizontal asymptote happening towards negative infinity. And this one here, the limit as x approaches infinity of f of x equals negative infinity. This one's not a horizontal asymptote because negative infinity isn't a real number. So what this says is as my x values are getting bigger towards positive infinity, my function is going to go ahead and head towards negative infinity. So I'm going to go down towards the y values, negative infinity over here. But I just want to be careful. I do have one other condition over here, f of 5 equals 0. So this is saying where to put a specific point. So put a specific point at the x value 5 on the y-axis at 0. So I'm going to go ahead and pick up where I left off here. and then take my graph and head down towards negative infinity. So as x values go to positive infinity, so as I keep going to the right, I'm told that my y values keep going down. But I also had to satisfy this little piece right here, f of 5 equals 0. So when we're done with these graphs, always make sure it passes the vertical line test, which it does, and that we've satisfied all the conditions here, so our vertical asymptotes, our horizontal asymptotes, and keep in mind that our graphs aren't going to look the same. There were some different options that we could have taken for sure, you know, the middles of the graph. As long as they pass the vertical line test, though, they are fine. They're still functions. Now we're going to look at an example where we evaluate a limit at infinity of a rational function here using this method that we have for solving limits at infinity. So I would consider this the long way. The first thing we're going to do is divide each term in the function by x raised to the highest power of x found in the denominator, and then we're going to go ahead and simplify. So in this example, the denominator's highest power of x is x to the fourth. That's why we're dividing each term by x to the fourth. So we have the limit as x approaches infinity of 2x to the fourth over x to the fourth minus 5x over x to the fourth plus 1 over x to the fourth, so remember each term, over negative 5x to the fourth over x to the fourth minus 8 over x to the fourth. And it also says to simplify each of these. So the next step would be the limit as x approaches infinity. We'd get just a constant 2 after some simplification, right? These are going to cancel. The next one will have minus 5 over x cubed. One of the x's will cancel there. Then plus 1 over x to the fourth. Over, on the bottom we have a constant negative 5. So we had, again, another cancellation completely there. And then minus 8 over x to the fourth. So we went ahead and divided everything by the highest power of x in the denominator, and then we simplified. So now what we're going to do is determine the behavior of each piece of the function by evaluating each term as x approaches positive or negative infinity. So in this example, as x approaches positive infinity. So for step 2, evaluate each term as x goes to infinity. So here was where we left off. Well, we're taking the limit of each individual piece. So here it is all written out, and we evaluate each one separate. While the limit as x approaches infinity of the constant 2, well, that's just the constant 2. So this piece here is just positive 2 in the numerator. And this second limit as x approaches infinity of 5 over x to the third, well, I have a constant over x to a positive rational number, so we know that this limit in the middle goes to 0. As does this last one here. I have 1 over x to the fourth. So again, as x goes to infinity, this limit is also 0. So each of these are 0. So it's like 2 plus 0 plus 0. And then in the denominator, I have x approaches infinity of negative 5. Minus the limit as x approaches infinity of 8 over x to the fourth. Well, again, the second limit goes to 0, a constant over x to the fourth, but the first one is just a constant. So it's going to stay negative 5 plus 0. So all that's left is 2 over negative 5, or negative 2/5 as the final answer. So it turns out this original limit at infinity has an answer of negative 2 over 5. One of the things I just want you to take a second to notice is that if you look at the function, I have a rational function, and the degrees of the numerator and denominator are the same. So if I look at those leading terms, the degrees are the same, and the leading coefficients over each other, 2 over negative 5, form the answer. So that is a way of finding horizontal asymptotes, thinking about if the degrees match, then the end behavior of this rational function is that towards positive infinity, I get close to negative 2 over 5. Alright, here we go with some more examples. So evaluate the following limits at infinity. But now we're going to use kind of everything we know. We're going to use the notion of end behavior. That's what these limits at infinity represent. And we're either going to apply graphical or numerical strategies when it's appropriate based on the function. If given a rational function, use prior knowledge for finding horizontal asymptotes. We don't have to do that long way. We could have obtained that answer if we knew some past knowledge about finding horizontal asymptotes if I have a rational function. So let's get started. In this first example, we're evaluating the limit as x approaches infinity of a cubic polynomial, negative 2x to the third plus x plus 1. So I'm actually going to go at this from a graphical perspective first. So I have a cubic polynomial. The leading term here is negative 2x to the third. So what I know about cubic polynomials is their general shape, and since there is a negative in front, there's going to be a reflection over the x-axis. So a generic cubic flipped over the x-axis is going to look something like this. So I'm not super concerned with exactly how it looks. I'm just doing a general shape, because now what I want to know is, well, what's going on as x goes towards positive infinity? Where are my y values going? Well, we can see that they are headed down towards negative infinity. So the answer to this limit is negative infinity. And that's from a graphical approach. Now, if we wanted a numerical approach, we're still focusing in on that leading term. That's the dominating term here. And if I think about substituting in, so if I think about the fact that x is going to infinity, if I think about starting to plug in values for x that are really big, so if I start to plug in 1,000 or 1,000,000, well, 1,000 to the third power is a really big number, and since it's multiplied by negative 2, it's going to head towards negative infinity. If I plug in 1,000,000,000 and cube it, but multiply it by negative 2, it's going to head towards negative infinity. So there's kind of those two different ways of thinking about it. In this second example, the limit as x approaches infinity of arctangent x, here I would say that we are going to go straight to the graph, because if I start to think about what happens when I plug in 1,000,000 into arctangent x, this isn't a function that we can easily think about what that specific number is, or even what type of number that is. But arctangent is a graph that we should be familiar with. So if I think about the graph of arctangent, and it's just a rough sketch, I have horizontal asymptotes at pi over 2 and at negative pi over 2. And it looks like the graph of the cube root of x. So as x is approaching infinity, what's happening to the y values is that they're getting closer and closer to that asymptote up there of pi over 2. So that one relied strictly upon knowing the graph. Looking at the third example here, I have the limit as x approaches infinity of, on the top I have a polynomial, a cubic polynomial, x cubed, and on the bottom I also have a polynomial, but it's not been distributed out. So I have x squared plus 1 all squared. So I do have actually a quartic polynomial, a degree 4 polynomial. And in this case, since I have a rational function, I can actually think about the horizontal asymptotes, if I remember that, if I have that prior knowledge. So the denominator here, I'm not actually going to bother multiplying it all out. I'm just going to remember that it's an x to the fourth, right? So it would be 1x to the fourth plus some stuff if I multiplied it all out. But the reason I'm doing that is because I'm focusing on the leading term of the numerator and the leading term of the denominator. So essentially, if the numerator's degree is less than the degree of the denominator, and it is, 3 is smaller than 4, then the horizontal asymptote is 0. And this really comes from what we learned earlier, that if the numerator is growing slower than the denominator, so in this case a cubic is growing slower than a quartic, a degree 4, then the whole fraction goes to 0. So it's kind of like I can think about it as the numerator is x cubed and the denominator is x to the fourth. So if I simplify that, well, that's 1 over x. And I know 1 over x goes to 0 as I start to plug in numbers towards positive infinity. So that's the rationale that's going on in our mind so that we can do this a little more simply rather than that long way of dividing every term by the highest power of x in the denominator. So if I go ahead and take a look at the fourth example, here I have the limit as x approaches negative infinity, and I have 3 plus 5x minus 2x squared, so I do have a polynomial on the top, quadratic, and on the denominator I have a linear function, so 3x, so also a polynomial. So I have a rational function. So I can think horizontal asymptotes, or I can really think about comparing the degree of the numerator and the degree of the denominator. Well, this time the numerator has a degree of 2 and the denominator has a degree of 1, x to the first. So the numerator is growing bigger faster than the denominator. So I actually am not going to have a horizontal asymptote. That's what we would have said in like a precalculus class. There's no horizontal asymptote. But that's not the answer to this problem. What we have to do is think about, well, if the numerator is getting bigger faster than the denominator, the answer's got to be infinity, right? The top's getting really big and the bottom isn't. So if I just think about taking the leading terms, if I think about negative 2x squared and 3x. So here, if I even reduce to negative 2x over 3, if I think about what happens as I plug in negative infinity. So if I were to plug in negative 100, well, a negative times a negative is a positive. So the top is going to be a big positive number. It's going to get bigger and bigger. And the bottom is staying constant. So this whole fraction goes to positive infinity. So there's a little bit of thinking about that we need to do to decide if it's positive or negative infinity. And that's when the numerator is growing bigger faster than the denominator. Let's look at a few more examples. So the limit as x approaches infinity of the square root of x over the cube root of x squared. So let's go ahead and rewrite these as fractional exponents. So the limit as x approaches infinity of x to the 1/2 and then x to the 2/3. So we can actually do a little bit of reducing here. So this is the limit as x approaches infinity. I would subtract 1/2 from 2/3, so subtract the smaller fraction from the bigger fraction. So it's going to end up leaving a 1 in the numerator and an x to the 1/6 in the denominator. So if I do that work there, I can clearly see that I have a constant over x to a positive rational exponent as x goes to infinity. So this denominator is going to get bigger faster than this constant, which is 1. So the whole answer is going to be 0. Although you didn't have to show this work or do this work if back here you could convince yourself that 1/2 is smaller than 2/3, and so the denominator, x to the 2/3, will grow faster than the numerator of x to the 1/2. So we can still do that comparison to determine that the limit goes to 0. In this example here, as x approaches infinity, I have negative 3x minus sine x, and then over 5 minus 2x. So we have this new feature, a trig function involved inside. So I have sine x. So if I think about, I want to know ultimately what's that dominating term in either the numerator or the denominator. So in the numerator, the dominating term is actually going to be negative 3x. So how do we know that? Well, let's think about the graphs for a second, or the graph of sine x anyways. So we'll do that scratch work right here. The graph of sine x bounces between the y values 1 and negative 1. So those are all the outputs of sine x. So sine x isn't going to dominate this function. As I plug in values towards positive infinity on the x-axis, the y values are just bouncing back and forth between negative 1 and 1. So the dominating term here is negative 3x in the numerator, and in the denominator it's negative 2x. So now we would compare those two leading terms, and since they have the same degree, we would take their coefficients over one another. So we would take -3 over -2, which of course simplifies to +3 over 2. And now we have the limit as x approaches infinity of the square root of x to the 4th plus x over x squared minus 1. So we can clearly see the denominator is dominated by x squared. But we have this new thing, the square root of x to the 4th plus x in the numerator. So what we have to do is think about the fact that what's going to dominate the numerator is the square root of x to the 4th. This plus x is not going to dominate. It's got a degree of 1 underneath the radical. So the bigger one is x to the 4th, but I have to keep in mind that it's the square root of x to the 4th. So let's go ahead and do a little bit of review and think about what is the square root of just x to the 4th if I think about it. Well, it's actually the absolute value of x squared. So whenever I take the square root of x to an even power, these absolute value bars come out. Except that in this case, having absolute value bars is kind of redundant because x squared will already be positive. I'm squaring something, making it positive. So the top is essentially acting like x squared. So I'm kind of just writing this below as a little bit of scratch work to help us think about it. So the top, I'm going to do this. I'm going to put is sort of acting like. So it acts like, it behaves like x squared. That's its dominating term up there. So if its dominating term is x squared and the denominator has an x squared, they're the same degree, then we take the leading coefficient over the leading coefficient. So the answer here is actually just +1. And we'll do one more with the square root function. So I have the square root of x to the 6th plus 3x and then over x to the 3rd minus 5, but this time we're approaching negative infinity. This time we're approaching negative infinity. So in the numerator here I have the square root of x to the 6th. That's the part I want to focus on, do a little scratch work on. So the square root of x to the 6th, again, whenever I take the square root of x to an even power, it's going to be the absolute value of x cubed. And the absolute value bars absolutely have to stay on this particular example. So they are relevant. On the other one, if I square something, it already makes it positive. But if I cube something, it could be negative, and I am plugging in negative numbers here, so it's important to keep those absolute value bars. So the top of this function here is essentially acting like the absolute value of x cubed. That's how we're thinking about it. And the denominator's dominating term is x cubed. So if I think about what happens as I plug in negative numbers, so something like, let's say -100, let's actually plug in a specific value. So if I plug in x equals -100, so the absolute value of -100 cubed, and then on the bottom I have -100 cubed, because just those dominating terms, that's what we're thinking about. So the top is going to be +100 cubed. I'm not even going to bother writing out that number because the absolute value bars make it positive, but the negative on the bottom is going to stick around. So it's going to end up being -100 cubed. So 100 cubed and 100 cubed, those are the same numbers. So I end up just getting a 1 and a 1, but there's that negative there. So the answer here is just -1.